All right, so it says a boat is moving at 25 meters per second at a heading of 35 degrees east of north relative to the water. However, the current is moving at 10 meters per second, 5 degrees south of east. What is the motion of the boat relative to the shore? Okay. I think the first thing I would encourage you to do is kind of what we talked a little bit about yesterday. Let's plan for this problem. Let's do a little bit of planning. I know that I'm going to have to take two vectors. I'm going to have to break them up into the x direction and the y direction. That's going to be the future of this question. And the two vectors are going to be the boat and the water. And I will be adding those together to get my answer that will be in rectangular. And I will eventually have to convert that to polar. So I am planning for what's going to happen. Good there? With that plan, I'm going to start by breaking each of these vectors into their components. Now, my intention here is to skip some steps because, well, I've been practicing my trig and I've gotten quite good at it. But if I skip a step that you need to see, just give me the sign. It's okay. I'll just go back. So I do like to make sure that we have some points of reference, so I will draw these little things out here, and I'm going to say, all right, let's start with the boat, which is 25 meters per second at a heading of 35 degrees east of north. So I'm gonna draw a fake triangle, or a fake thing, because I'm not really drawing it to scale or anything anymore. That was fun for yesterday, but let's just get to the problem. So this is, oh, that's not east of north. Let's draw it east of north. There we go, now I'm east of north. Good. Let's put in the information I have. I have this 35 degrees and this 25 meters per second. I'll leave the units off for right now while we're working the problem. Now, I need to find out how much of this velocity is in the y direction and the x direction, so I am going to create component vectors by wrapping a triangle around my angle. There, I've wrapped a triangle around my angle. This is just it's just something for me to hang my numbers on so I can see what I'm doing and try and keep track. Some of you don't need this, but you guys who are visual learners probably do. Something that you can visualize what's happening. I've been doing this for a while now and been practicing, and I've recognized that I can just look at this triangle, knowing that this is the adjacent side and the opposite side. I can say that this one's got to be 25 sine 35, and this one's got to be 25 cosine 35. I'm skipping a few steps there. I'm not writing out sine, cosine, tangent, but am I okay to do that, or do you need me to write those things out? We're good. All right. It looks like they're both positive because it's in the first quadrant, so I'm going to go ahead and write my vectors into my chart as 25 sine 35 in the x direction plus 25 cosine 35 in the y direction. I know I can get numbers for this, but one of the things I also want to start encouraging you to do is not be scared of writing it out like this, because in the very near future, you'll be writing these out with like placeholders. So it might be x sine theta and not 25 sine 35. And get used to seeing that this is just a number, right? So we'll get the number portions done in a few minutes. So that one's good. We're done with the boat. Let's go on to the current. So I don't need this anymore. I don't need that anymore. The current is 10 meters per second, 5 degrees south of east. So that's 5 degrees south of east. And this whole thing is 10 meters per second. So again, I need to find out how much of this is in the x direction and how much of this is in the y direction. So I will wrap a triangle around my angle, making sure that I have, a right triangle here. Again, and I'm going to do this because I think it'd be a good idea from what I just saw. Sine of 5 degrees, cosine 5 degrees. And this is going to be opposite over hypotenuse. And this one's going to be adjacent over hypotenuse. So looking at my triangle, this looks to be the opposite side, this looks to be the adjacent side, this looks to be my hypotenuse. So I can come back up here and say, all right, this is going to be 10, this is going to be 10. And now this has to be 10 cosine 5 degrees. And this has to be 10 sine 5 degrees. Okay. Just work the triangle a little bit more thoroughly for a couple of students I think need to see it. But I think I'm good now. Got all the pieces in place. Let's go ahead and fill in my chart, but be careful. This one's pointed down. We're in the fourth quadrant, so my y value is going to be negative. So 10 cosine 5 degrees in the x direction minus 10 sine 5 degrees in the y direction. Part of the reason I wanted to write all these out is to reinforce something from the other day. Don't use your math class as your basis here. Notice that x doesn't mean cosine and y doesn't mean sine, right? Do you see it now? Is it clear? So you just have to base your angles on the situation that you have. But now I'm just going to do some addition. I'm going to add down this column and down this column. This sounds like work for a calculator to do, doesn't it? So I don't think there's any algebra there, but you do have to now work the numbers into your calculator. So, we all good? All right. So this is the actual velocity of the boat relative to the shore, but it's not in polar, it's still in rectangular. So I need to express my answer in terms of a magnitude and direction. So again, I'm gonna put one of these up here so that I can do that. But this time I have a set of directions here. And I don't have to go in this order. It doesn't matter which order I go in. So I can write the y and then the x if I'd like, or I can write the x and then the y. Does anybody have a preference of the order I put these in? Okay, if there's no preference then, and I'm gonna go 24.3 in the x direction, and then 19.6 in the y direction. And my vector will then be something like that. Now, this part, not a big deal, but if you had gone in the other direction, meaning you did your 19.6 first and your 24.3 second, we would just be dealing with two different angles, right? That's the only difference. But be careful. I want you to understand something here that is important. You would do the inverse tangent here to figure out what your angle is going to be. This side's going to be 19 divided by 24.3. The other side's going to be 24.3 divided by 19. They're inverses of each other. With the tangent function, that just gives you the complementary angle. But trust me when I say, if you're writing a multiple choice test, they know that. And so often one of your distractors will be what happens if you reverse this and don't know you reversed it. Because by reversing this, you've actually reversed all of your trig functions. So be careful. That's an oft used distractor to see if you know your trig. All right, here we go. So I need my total, which is going to be the square root of 19.6 squared plus 24.3 squared. That's where we're going to get our 32 meters per second. But I need to get my angle as well. So I know tangent of theta is going to be 19.6 divided by 24.3. So that's, again, one of those grab your calculators and have it tell you the answer kind of thing. And I get 39 degrees. Have to provide reference. This 39 degrees is starting at the east and turning towards the north. So I am north of east. All right. Yeah?
For the hypotenuse, I got 31.2. Why did you round it up?
It might be 31.2. I was calling it from memory.
Oh, okay. I was just a little confused.
I said, you do a lot of these after a while and the numbers become blurry. All right. If you can't do this, or if you're having trouble with this, I posted 3. They're the AP Physics 1 practices. They are just this over and over again. I will send out the answers too. you need to practice. And I'm not giving it as homework, I'm giving it as practice. I have an actual homework you're gonna get today. It's the level that I want you to work at, which is what we're gonna do next, okay? This is the kind of problem I want you to be able to do. You see, these problems that we've done are just like I'm pointing myself one way and the water or the wind is going another. But what if you actually wanted to go a specific direction and you had to deal with the fact that there was wind? So an example I'm going to give is, what if you were trying to land on a runway and you need to be going this way to land on that runway? If the wind is going this way and you point yourself along this runway, are you going to be able to land on that runway? Very unlikely. Is it pretty clear the only way you'll actually land on this runway is if you point yourself a little bit to the west? Now, you have to do the problem this way. So this is what your homework's going to be like, all right? So I want to talk to you about how to do this. And again, like I said, I have a pilot in the room. Planes don't point their nose towards the ground to land. That would be bad for everybody on board. In order for a plane to land, you have to understand the way lift works, and lift works because you have air moving over the wings. If you increase the rate of flow of air over the wings, you get more lift and the plane goes up without pointing its nose up. There's a force on the wings that push it up. Well, you can do the reverse of that. You can slow the plane down. If you slow the plane down, the lift becomes less, and therefore the weight of the plane pulls the plane down. Now you adjust this because you don't want to come down too fast or too slow. And I'm simplifying what is a more complex procedure because there are things like flaps and other stuff that are a part of this. But the whole idea is to bring the plane down so that it's relatively level when you get close to the ground. It's more comfortable for the passengers that way too. Now, planes have a minimum safe speed for landing. So if we say a plane, and these numbers are made up. I always use numbers that are big enough for you to actually calculate and easy enough for us to deal with in the classroom. So if I say the plane has to be flying at 120 meters per second to land, that's not true at all. That's way too fast for a plane to land, because that's somewhere around 260, 270 miles an hour. Planes are usually going slower than that upon landing, or they wouldn't be able to stop on a runway. So a lot of the numbers I choose are not realistic. They're for demonstrative purposes in class. And one person knows that, but many of you probably would know that too eventually. So let's ask the expert. The plane you flew, what was your general landing speed?
Landing is about 60 to 65 knots.
And a knot is, because they don't know what a knot is. It's a nautical mile per hour. Knots are a little bit faster than saying miles per hour. So you said 60 or so knots?
Yeah, 60 to 65 knots.
So that would be somewhere around 34 to 33 meters per second. I don't want to use that number. I'm going to use something bigger than that, okay? Because it's just easier for us. I'm going to say that our landing speed is 120 meters per second. Again, just because making the numbers big enough, you can see the exchange of vectors a little bit easier. And I'm going to make the wind a catastrophic 40 meters per second. You would, because that's around 90 miles an hour. We're going to land our plane in a hurricane. It'll be fun. But again, just making numbers big enough so we can see the results of the vectors on our numbers, okay? Now, let's also say that the angle of the wind is, we'll go with 40 degrees east of north. Enough of that. This problem is no different than what we've done before, except that we don't know the heading of the plane, right? We don't have this. It's theta. I think we can guess kind of what quadrant it has to be in, but I used to say that, and I found out last year that some students had a difficult time with this guess. So I'm confused by that, quite frankly, but let's consider for a moment, which quadrant do you think the plane's velocity would have to be so that it could be traveling north down the runway, but also counteract the wind? Hold up the number of fingers for 1, 2, 3, or 4. You know the numbers of the quadrants, right? Maybe not. I just saw that look. 1, 2, 3, 4. Which one do you think it has to be? All right, so we are not in consensus, but remember, the wind is going to push the plane this way. If we think about the wind for a moment, it's got a component of its velocity this way, and the wind has a component of velocity this way. We would like the plane to have no component of velocity in the X direction in order to land on the runway. So the plane needs to point itself this way to counteract the fact that the wind is pushing it this way. So I'm going to go ahead and answer my own question and say that we want quadrant 2. I want to point the plane that way. That way there will be a component of the plane's velocity in the negative x direction to counteract the fact that there's a component of the plane's velocity, a component of the wind's velocity in the positive x direction. I don't care about the fact that the wind is pushing the plane down the runway. I might care if the wind was pushing the plane against the runway. That could make for a difficult problem too. Now let's work the problem, but let's also understand that in working this problem, I'm not going to change the procedure. The thing about any procedure I give you is that it should work in all circumstances, and it will work in this circumstance. Meaning procedure 1 is still to lay out your vectors and break them up into rectangular components. So I'm going to have, just put that anywhere, I'm going to have the plane's and the wind's velocities here. And I'm going to eventually add them up, and that will be the resultant. The difference is, when I add them up, I know ahead of time that this one's going to be 0. Right? I want the x velocity for my resultant to be 0. That way it has no component going left or right. Does that make sense? So that's the difference. I'm still going to do the same procedure. I just happen to know part of the answer already. So there'll be 0 in the x hat direction. That way I land on a runway. If my plane has a velocity in the x hat direction, it's falling off the runway. It's either going to the right or to the left. You guys follow? But we're still going to add up our vectors. So let's follow the same procedure. I'm going to put a placeholder in here, theta, and 120 here. I'm going to wrap a triangle around my angle. So same as before, wrapping my triangle around my angle. I'm going to recognize this is the opposite and this is the adjacent. I'm not going to write sine and cosine all the way out. I'm going to say the opposite side is 120 sine theta, and the adjacent side is 120 cosine theta. Now I could have picked here to measure my angle. I just chose one. You have to pick something, so I just picked that one. Now those are my components. Any question about where I got any of that from? Go ahead.
Where did you get the 120 from the sides?
So that the speed of the plane is 120, so I made that my hypotenuse. Is that cool? All right. So now for the plane, I'm going to say negative 120 sine theta, because it is in the second quadrant, so it's got a negative x component, plus 120 sine theta in the y direction. So that's my vector information for the plane. Any question about where I came up with any of that? Yep. It would be cosine. That's a good question. I should write down what I put on my paper. Well, fake paper. Keep going? Well, I still have to do the wind. So we'll take this, put it away, and go ahead and do the wind next. So let's talk about the wind. The wind has a velocity something like that, and it is 40 degrees east of north at a speed of 40 meters per second. Again, I'm going to wrap a triangle around my angle. This is my adjacent side, this is my opposite side. Using all that fancy smancy trig, I will get 40 sine 40 degrees and 40 cosine 40 degrees. Any questions about those? I know there's numbers, so we'll get to that. So I'm going to go ahead and put that in here. 40 sine 40 degrees in the x direction plus 40 cosine 40 degrees in the y direction. You all feel good about this? Go ahead.
I just want to ask really fast. I didn't understand how you got the 120 negative beta. How is that negative?
It's because of the direction. So this is negative x, this is positive x, and the plane has a component that's pointed towards the negative side. You're welcome. All right, so I'm just going to move this over here and realize I'm still doing the same procedure. I've converted all of my vectors into rectangular from polar. Now I'm going to add down the columns, but in adding down this column, I just know the answer is going to be 0. So I'll write out minus 120 sine theta plus 40 sine 40 equals 0. You just solve this for theta. But I did find that it would be best if I do some algebra here. And that's probably true in this room too. So I have choices about how to do my algebra. I can figure out 40 sine 40 first if you'd like, or I can leave it there till the end. But I have something else to show you, so I'm going to go ahead and do my 40 sine 40 first. I get 25.7. So I'll subtract my 25.7 from both sides. And this is way more algebra than I like doing. I'm doing it for the benefit of somebody in the room, probably more than one somebody's. I'm going to divide by negative 120. All right, so we see what we have here. Not too terrible, right? So I'm going to the negatives cancel out. And I'll take the inverse sine, and I get 12.4 degrees. Okay? All right, before you move on from this, there's something you need to see. Let's take this step right here. What if this was, and you worked the numbers out correctly, and this was 257 over 120, okay? So that you had sine theta equals 257 divided by 120. Put this in your calculator and figure out the angle, please. You need to see this. You see the thing your calculator just told you? Don't throw that away. Don't think you did something wrong. If you work your problem out and you get to this point, what your calculator is telling you is exactly the truth, that there is no angle that can make this sine. Sine can never be bigger than 1. And this number is clearly bigger than 1. What they're saying in this case could be that there is no angle the plane can point at that will safely allow the plane to travel against the wind. The wind's too strong. It's saying there's just not, the plane must not have enough velocity to counteract the wind. So keep in mind, this kind of answer doesn't necessarily mean you've done something wrong. It might mean that the answer is there is no angle that will safely allow the plane to land on that runway. So be aware of what happens when your calculator gives you an error message. It doesn't always mean you did something wrong. Okay? Just keep it in mind of what it will look like on your calculator when no angle will satisfy the relationship. And that's true for sine and cosine. There will always have to be a number between 0 and 1. They are always scaling your value. All right, back to work here. We have our angle, 12.4 degrees. That means we know two things. First, our plane will actually have a heading of 12.4, and we know that that's going to be west of north because that was our picture of our plane. Right? We are pointed west of north. So that is the heading of the plane. And if I want, I can say this is 120 this is the plane's original vector of flight. Now, if we add these together, now that we know the plane's angle, what we will have left is how fast the plane is going relative to the ground. This will still be the plane's velocity along the ground, because that's what adding these two vectors was, our chance to see how fast the plane is going. So one of the things you might be asked as a part of this question is not only what direction does the plane have to aim, but when it lands, how fast is it going relative to the ground? Does that make sense? So let's follow up. Let's complete the problem. That will mean taking 120 cosine 12.4 degrees plus 40 cosine 40 degrees. This will all be in the y direction. This is the ground speed of the plane. So I don't know what this is. Can somebody tell me what this is without me having to use my calculator? Yeah. 147.8 meters per second due north. Right, we planned it to be due north, so it has to be going north along the runway. Everybody good so far? So part C of the problem, the runway is 1,000 meters long. What acceleration will bring the plane to rest along the runway? You can see follow-up questions taking this now and making this like your initial velocity and work in the stuff from our prior problems. You kind of see that kind of thing? All right. I believe this brings us to the end of the class period. 3 practices will be posted today that are these questions, just like this, along with just the numerical answers. Please practice tonight. Tomorrow, I think I want to see if you can do this, okay?